Swayam Prabha. Digital India. Educated India.
So, welcome back. This is our concluding lecture of this course. So, I am very happy to say goodbye to all of you. If though I would have probably loved to teach single phase induction motor and DC motors also, in addition to whatever I have covered so far. But I have a sort of a feeling that I think around 45 hours of 45 hours of teaching is adequate at the first course level, and so and there are very good resources available for single phase induction motors like Fitzgerald, Kingsley. DC machines, you will get dedicated books also available to it. I mean, other standard books also do, of course, cover it, like Professor Pai's book also covers it, Fitzgerald's Kingsley covers it, MG Say covers it. So, many people do cover it. So, let us use this lecture basically to sort of recap what we did, and I do not exactly want to run with you lecture by lecture, but we let us see recap of what we did. We started with KCL and KVL, Kirchhoff's current law, Kirchhoff's voltage law. We discussed why electrical systems are so very popular, why human mankind is completely depending upon electrical systems. First we used it for lighting, then we used it for motors, then we used it for transportation of electrical trains and so on. Induction machines became the workhorse of in the industry. Then you had your refrigerators which use induction motor, compressors. Then you saw air conditioners, they also have induction motors and things like that. And now you talk of EVs, electric automobiles, and they are also now your even automobiles, scooters, everything are becoming electric. So the electricity is the thing, the beautiful thing that mankind has tapped from nature, and why we need it, we discussed it. And there is a very serious issue with respect to grounding and safety. It is a dangerous thing at high voltage, human body absolutely cannot take it. So, we discussed also 3-phase supply, we also discussed grounding and safety. And if you recall, I did even the balanced system and unbalanced system quite carefully, bringing out to you that in a 3-phase balance system, the instantaneous torque is equal to average torque, or instantaneous power is going to be equal to average power. So why we need multi-phase systems, why single phase system is not sufficient, we talked why we have 50 hertz systems, why US has 60 hertz systems, and we said that this is more a consequence of standardization, and we should not unnecessarily assign too much of physics based interpretation to it or economics based interpretation to it. North America has developed independently, Europe has developed independently, and Indian systems, because we carry a British legacy and therefore are closer to this thing. So, what is explained by simple historical reasons should not be tried to be explained by physics. Then we also discussed what do we mean by in a single phase system we showed that instantaneous power is different, pulsating, it has a double frequency component, while in a balanced 3-phase system this double frequency pulsation component is cancelled out, and so instantaneous power is equal to average power. So, when the instantaneous this thing is pulsating, it could even be brought to zero average. So, average and instantaneous power become different first of all once you have something DC and a double frequency pulsating component coming on it. But for example, if you connect a single phase source to a inductor or just a capacitor ideally, then the double frequency oscillation is transfer of energy from supply to this storage device which is a inductor or a capacitor, and then back, and this happens at a double frequency with a net zero in an ideal situation where there is no resistance. So, actually average power becomes 0, but instantaneous power is not 0, in which case how do you explain this V and I? So, we introduce the concept of reactive power, because it is happening because of the interaction between voltage and current. So, reactionary in some sense. So, we said this is a reactive power, while the power which gets consumed like what resistor does for example, or where a effective work gets done, for example, when an electrical vehicle moves from one place to another. So, that we said that is the active power, and average active power whose unit is watts joules per second is what is for the active power, the average active power, while the reactive power is simply product of V into I. So, and it is in our mind to emphasize that it is reactive, we said it is volt ampere reactive or VARs, and then P square plus Q square under root is equal to just the product of V into I, which we said is the apparent power. And then we said P plus JQ, where J is the square root of -1, we said that is called as the complex power. And even before we did all this stuff, I am like going forward, backward, this is a journey in the memory, what in my mind I think is important concepts that I brought out to you. We actually introduced to you phasors first. Phasors are a vectorial representation of the sinusoidal quantities, and it is based upon a very important underlying constraint that you can do vectorial addition of such quantities provided they are at the same frequency. So, if they are at the same frequency, then the time dimension can be abstracted out, and the angle which is associated with the sinusoid and the peak amplitude which is associated with it, these two things can be abstracted out as a vector in polar coordinate or rectangular coordinate. And then when you add sinusoids at the same frequency, maybe of different magnitudes, maybe of different phase angles, they can be simply mimicked by the vectorial addition, the parallelogram law of identity, and hence came the word phasor. Because we talk of single phase, 2 phase, 3 phase, and then we are talking of vector, together they come together and become phasor. And therefore, P equal to V I cos phi, where phi is the phase angle between V and I, and Q is equal to V I sin phi, the reactive power. These kind of expressions were derived, and the cos of phi is called power factor, not phi, but the phi is called the power factor angle, but the cos of phi is called power factor. And then because phi, whether it is positive or negative, it still cos of phi is positive. So, therefore, we said this requires an English descriptor in addition, like 0.8 power factor lagging or 0.8 power factor leading. And then we said that all these motors, because they have so much of iron involved in them, so they create a lagging power factor, and actually it appears that you should be doing V into I work, but you are only doing V into I into cos of phi, where cos of phi could be so 0.8 or something. So, that 20% stuff which we look at it as reactive power or something like that, not really 20%, 1 by under root of 1 square minus 0.8 square is about 36% or something, because there is a notion of quadrature and not just a simple addition which is involved when you are talking in terms of cos phi's and sin phi's. So, that part of the current is still creating I square R losses, right. So, when it goes through your transmission line and the distribution line, the active part also creates I square R and the reactive power part also creates I square R, and therefore, unnecessarily the reactive power part, though it does not help us in doing any effective work, it causes a grid to lose more amount of power, and this loss has to be borne by society. So, we said that therefore, distribution systems usually enforce a requirement of distribution systems therefore enforce the requirement of power factor correction to the end user, and say that your power factor should be close to unity, otherwise we will penalize you for poor power factor, because you are the one who are increasing loss in the distribution system. And when that loss increases, obviously voltage regulation also becomes poor. And how can we achieve this improvement in the power factor? So, we discussed that a parallel shunt capacitor is a good way of doing it, and that can be done for a single phase system also, that can be done for a 3-phase system also. So, that is the next thing that we had talked about. We also when discussing 3-phase systems, we also discussed delta connection and star connection. The star connection has the advantage that the star point can be grounded for safety, delta connection does not have that. So, the neutral in some sense is floating, or floating neutral or something like that happens there. So, this is some of the basics of the single phase system, 3-phase system, why electrical energy is used and all that. Then the question also was, how do I, means if inductance plays such an important role, how do I characterize the inductance? It is a circuit parameter, but it has to be connected to the physical geometry. So, we need to, we dived deeper into the concepts of the magnetic circuits. We introduced the notion of the magnetic circuits, and we dived deep and brought out reluctance as an analogous quantity to resistance in the DC systems, and then magnetic circuits are analogous to the DC circuits that we come across, or AC circuits that we come across. Then we talked of KCL and KVL equivalence using fluxes, flux line, and we talked of B H, B equal to mu 0 mu r H as or sometimes BH curve, which is for a iron which undergoes saturation. So, we discussed the saturation behavior also in the BH curve. Then we defined knee point and said that usually we will like to design everything in the linear region below the knee point. And then once we had reluctance, we also designed the notion of permeance, and through magnetic circuits we defined, for example, that the self inductance can be written as n square by the reluctance, where n is the number of turns associated with the coil. And once self inductance was done, then we discussed mutually coupled coils, and once then getting into the mutually coupled coils, we showed that if they share a reluctance of pathway, their common path has a reluctance R in simple geometries, then the inductance is given, mutual inductance is given by N1 N2 by R, where N1 is the turns on the first coil, N2 is the term on the second coil. And so, therefore, in an ideal case, mutual inductance is simply the square root of product of the self inductances of the each coil, but then there will be leakage effect which was introduced, which is like some flux starts from the first one, but does not link the second one, and that is vice versa. So, therefore, there is a coefficient of coupling, and M is equal to K times under root of L1 times of L2. So, this was where K is less than 1. So, this aspect was introduced. Once we had mutual coupled coils, then again the direction of winding it decides, when we put the dots, whether the flux are properly additive or not. So, dot convention was introduced, and it was said that what dot convention says that if at the outside, if I have marked the 2 dots for the 2 coils and the currents are entering the dots, then the fluxes that they will create will have a additive additive configuration or a direction, and there this helps us basically not to every time open the box and see how the winding is done, and when the current is entering whether the fluxes created by them, mutual fluxes, they will be additive or subtractive. All that we do not have to do once we put the proper dots on it. And then once we have put the dots on it, then we worked some examples of it. You can have L1 plus L2 plus 2M for example in a series connection, or you could have net effective inductance as L1 plus L2 minus 2M. We did quite a few examples around it, and then we talked of energy stored in a conductor and energy stored in two mutually coupled coils, and then subsequently we went on to the concept of hysteresis, and we showed that it creates a loss because of the nature, it becomes a dissipative thing. So, the hysteresis loop was on the BH curve was developed, and we said that hysteresis loss is proportional to the AC frequency, depends upon the iron material and so on and so forth. And then another thing we talked of is eddy current loss, and the eddy current loss is because this iron or any such material is has a very low resistivity. So, even small induced EMF there by the rate of change of flux will create significant amount of currents to cancel it, which are like eddies which you see in water or any other fluid, and so they are called as eddy current losses. And later on in transformers we said therefore, we should laminate the core to cut down on the eddy current losses, but the hysteresis losses can only be improved or controlled by proper design of the by proper choice of the magnetic material. Then we basically also talked of single phase transformer, and in the single phase transformer we had single phase transformers, dot conventions, everything put on. Our main focus was understanding its operation was really not such a big challenge, but the thing was we wanted to develop the equivalent circuit of the transformer, and that equivalent circuit to begin with looked like something like a T circuit with primary leakage reactance, secondary leakage reactance, primary resistance, secondary resistance, magnetizing impedance, magnetizing resistance, or rather losses resistance which is associated with the losses in the core, and we developed that magnetizing circuit. We had that dash notation, remember, transferring for example an impedance from secondary to primary causes you to multiply the effective resistance seen is, or effective impedance is seen is A square or N1 by N2 square times of Z2 and all that. And actually now that I say mention Z2, even before all that I talked of reactance, impedance, how the DC circuit laws move on to AC circuit laws, how do we add impedances in series circuit, how do we work similar to the resistance, how do we calculate effective impedance in a parallel circuit, which is how we showed that you can add admittance in the parallel circuit, and then the KCL and the KVL has proper application or analogy happening with phasors also. So, phasors KCL and KVL are equally valid not only with instantaneous quantities, but also with phasors. Also we did while this theme was also going on, we had introduced basic generator concept. We had introduced the basic generator concept, and we talked of space distribution of B in the air gap, and we talked of the Fourier analysis of it, and we talked of amplitude of induced EMF and the RMS value. I had not so far mentioned in my recap so far RMS value. To begin with, we had said that phasor can be talked of as amplitude and angle in polar coordinates, but then in expressions like Vi cos phi, Vi sin phi for P and Q, what we take is the RMS value, the root mean square value, and therefore, later on we said that power engineers do not use amplitude, but actually use amplitude by root 2, which is the RMS root mean square value as the magnitude of the phasor. So, this is an important point that we talked of. Also, I had done quite a bit of math recap in terms of Euler's identity and talked of in phasor analysis, d by dt operator can be replaced by j omega, the integral operator can be replaced by 1 by j omega, and we looked at the integral differential equations, but we said our focus will be only steady state and transients die out, and we will not look into it due to presence of resistance. And then complex numbers, we talked of Euler's identity and many interesting things around that. So, this unbalanced systems also would show that the net torque or power becomes has a still a oscillating component associated with it. We did quite a few number of solved examples, and we showed how when we are talking of 3-phase system star or delta, the general power expression can be written as root 3 VL IL cos phi, and the general 3-phase Q expression can be written as root 3 VL IL sin phi. So, we looked into that, and we said that if the system is balanced, you can have a 2 wattmeter method for calculating the power and power factor. You can calculate in the using just 2 wattmeters instead of 3, but also I made a comment there that what if your 1 wattmeter is having some error. So, usually 3 wattmeter basic approach would probably be a good approach when you are doing instrumentation. Try to do as much instrumentation as possible, so that if there is any error in your instruments or any problem, you will be able to figure out. But 2 wattmeter method is a very beautiful method used in experiments and other places for calculation of the 3-phase power using just 2 wattmeters, and we talked of that. And then we talked also of the fact that the no load magnetizing current of a transformer is very low, voltage regulation of the transformer can be kept low, and the leakage reactance of the transformers can be kept low. But of course, magnetizing BH curve also we can control those values, but all these aspects we discussed. Usually I have not mentioned this in the course, this is a point which I am mentioning here, but usually when a utility goes and buys a transformer, for example a 3-phase transformer, then it also specifies how much leakage in reactance it wants, like 8% or 10% on its own rating. This it does because of the fact that if the leakage reactance goes very low, by mistake a short circuit happens, the short circuit current will go very high, and that could be a problem. So, to control short circuit current, a utility may specify while buying that I want approximately so much leakage reactance, and then the designers will handle that. So, all this, how do we measure? So, we said we have a equivalent circuit, but there should be some tests to measure those parameters. So, we talked of open circuit test and short circuit test, and usually you do these tests in the lab, and we talked of how that can be handled. And then efficiency we talked of regulation, we talked of auto transformers in detail. Then we went to 3-phase transformers, different types like core type transformer, shell type transformer. Then we went to Y delta and transformers, and we discussed the 30-degree phase shift that happens in these, and the motivation for trapping zero sequence currents and things like that. We discussed those things when we talked of the star delta transformers, and then we did couple of numerical examples, and we even did three phase winding transformers and zigzag connection. So, we actually explored transformer in a lot detail. Actually, if you look at it, I have done quite a bit of single phase, three phase, auto, three winding transformer. So, we have done quite a bit of it. Then we talked of alternators, their windings. Detailed explanation of the alternating windings was given. We talked of cylindrical rotor construction, we talked of salient pole construction, 2 pole, 4 pole, 6 pole alternators, which ones are used where, and then one very important concept of this course is that if you have a 3-phase distributed winding in space and you have a 3-phase distributed current in time, then it causes a rotating MMF in the field. And when you say it causes a rotating MMF in the air gap, so distribution also causes each individual coil's voltage will be phase shifted vis-a-vis concentrated coil, and so this phase shift will cause net effective voltage developed to be a bit below the concentrated one, but the advantages are that in the flux waveform there are no harmonics which will trouble you for some other things like losses, parasitic torques, losses, and so on and so forth. So, this will reduce the net effective voltage with respect to the concentrated winding. So, we introduced distribution factor for the AC windings. We talked of eliminating harmonics, particular harmonics, by short pitching the windings, and then we had a general overview of a 3-phase induction motor. That is what we did. Then if you recall, we also looked at very basic electromechanical relay, the Lorentz law, the force and torque calculations, and for this I introduced the concept of energy, magnetic field energy, and correspondingly lambda I minus Wm gives me the co-energy. So, another concept which was introduced, very machine specific concept which is used, that you can also have co-energy defined such that Wm plus Wm dash is equal to lambda times of I for a single coil kind of a system, and then we extended it to multi-coil system also, and then we derived that torque can be written as plus rate of change of partial derivative of the rate of change of co-energy with respect to x or theta as is the applicable this thing. And this example we used for these examples, then we solved examples of different how to calculate torque when you, for example, magnet pulls up something, how to calculate the force of attraction, or even this same concept we have used for deriving 3-phase induction machine, or rather single phase 2 pole machine, calculating the torque which is associated with it. So, we talked of torque speed characteristic. Synchronous machine torque calculation we did using the concepts of this using the notion of this energy and co-energy. I did a very detailed this thing, even for equivalent circuit of transformer also I did a pretty detailed job of its circuit approach, and I had a hats off to Professor Pai, whose book I used as my reference there, who has done it very elegantly, and it is very well done in Fitzgerald Kingsley also, and that is a wonderful thing. I really enjoy teaching torque expressions and equivalent circuits from energy co-energy principles, because there is very little waving of the hand or intuition playing a role in my analysis. It's good to have intuition, but the analysis, formal analysis should be very good, very pakka, very solid, and that is what is there. Incidentally, when I discuss 3-phase induction motor, I am not doing a review in the sequential order of the lectures, please, but trying to look back at important concepts that we have picked up. And in alternators we use this 3 by 3 matrix, 3 by 4, 4 by 4 matrices, mutual coupling between the stator windings, then the rotation of the rotor is there. So, how does that brings coupling concepts, and then how do you translate into calculating the net co-energy of the system, and then how do you take derivative of that, how do you take derivative of that with respect to theta and calculate torque and show that that torque can be a proper constant value and not a pulsating value. So, we did that, and once we had the rotating MMF concepts properly fixed in place, synchronous machine concept properly fixed in place, mechanical radians per second, electrical radians per second, those concepts put in place, then we started into induction machine, right. I mean, we started with a 3-phase induction machine. We discussed the torque speed characteristic. That is the end of the course. So, I am not going to go too detail into it. Usually all of you would remember what I did in the end of the course pretty well. So, we dived deep into the induction motor. We understood its principles from the physics, then we tried to understand it also from the point of view of energy and co-energy, but here I felt somewhat constricted because this is a first introductory course, and if I have to derive energy, co-energy and torque in that particular way for a 3-phase, not for 2-phase, for a 3-phase induction motor, then 3 coils on the stator, 3 coils on the rotor makes it 6 coils and a bit tedious. So, this is where I slightly backed off from this, and instead introduced to you the equivalent circuit of the 3-phase induction motor using generalized transformer ideas, that the induction motor is very much like a transformer, but there is an air gap. So, the magnetizing currents are higher and there is an additional degree of freedom for the rotor to rotate. So, the frequency on the stator side and the frequency on the rotor side is same, but whatever is induced on the rotor side will finally get reflected on the stator side at the stator frequency only. So, therefore, one equivalent circuit looking from the stator side can still be given, where the resistance of the rotor winding is written as R2 dash by S. So, the dash is still the same transformer concept of referring everything to the stator side. Then we talked of what is the maximum torque that can be developed, what is the slip at which it is developed, what are the problems of the starting, why the starting currents can be very high compared to the normal operating currents, and why the at synchronous speed for ideal machine the torque would be 0, and how to use this kind of a machine and how to measure their parameters. So, we talked of blocked rotor test and no load test, and finally, after solving certain set of problems with torque speed characteristic, equivalent circuits and so on and so forth, at the end I closed the story by discussing double cage induction motor and deep bar induction motor, and showed you that how we can alter the resistance. That is the very last class, how we can change the resistance during the starting. We can have a high resistance and then reduce it near the normal operating condition, so that at the time of starting you get high torque by getting the high resistance, but at the time of operation you do not want R2 to be high, because then it becomes a lossy thing. So, how that can be done, how you can exploit skin effect here. So, those beautiful constructions were given to you. So, this in nutshell was the basic course on power engineering 1 that we did. I hope you enjoyed this course, and I would like to thank all of you participants who participated in this course. I thoroughly enjoyed doing it. As I said, this is just the beginning. Probably I could have done DC machines also, probably I could have done single phase rotating machines also, and then there are linear machines, and there are many more novel. The technology just keeps going forward and forward. So, I could have done a few more things, but then we have to, due to limitations of the time, we have to stop somewhere, assimilate our understanding and say okay, the rest in future. I hope I have motivated you enough to continue with this subject continue with this subject later on, and you will dive deep into this subject in much more detail. Now even your EVs have become motors, right? So, you should keep going deeper and deeper into this. Your wind generators are after all motors. So keep doing this subject. Wish you all the best. Thank you, and that's it from here on Power Engineering 1. This is Shrivardhan Soman signing off on this course. Thank you.